Somewhere in the vast, silent reaches of the cosmos, a staggering emptiness stretches across space, nearly 1 billion light-years wide, hauntingly dark, and strangely quiet. This is the Eridanus Supervoid, an immense cosmic underdensity that aligns almost too perfectly with a chilling cold spot imprinted on the ancient light of the Big Bang. It defies expectations, unsettles models, and whispers of mysteries yet unsolved. Could this be a rare accident of the universe? Or is it the shadow of something far deeper, something that challenges the very structure of reality itself? This is where the story begins, a tale that stretches from the very birth of the universe to its largest structures and possibly even beyond the borders of our known reality. It begins with two mysteries, one from the dawn of time and one from the large-scale structure of the cosmos today, that appear to be intimately connected, though no one can quite explain why. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The cold spot was first detected in the early 2000s in data from the Wilkinson Microwave Anisotropy Probe, or WMMAP, which mapped the cosmic microwave background, the faint afterglow of the Big Bang. Scientists expected the CMB to be nearly uniform, with only slight variations in temperature. But in one direction, toward the constellation Eridanus, they saw something odd, a region much colder than expected. Too cold to be dismissed as a typical fluctuation. At first, it was thought to be just a rare, random blip in the early universe's thermal map. But then came the surveys. In 2007, astronomers noticed that the same region was also curiously lacking in galaxies. This wasn't just a colder part of the sky, it might also be emptier. That was when the Eridanus Supervoid theory began to take shape. A team led by Istvan Sapudi used data from galaxy surveys like the TUMAS and WISE catalogs to identify a large-scale underdense region in the exact direction of the cold spot. This proposed void was enormous, hundreds of millions of light-years across, and potentially capable of influencing the light from the CMB as it passed through it. The idea was that this immense cosmic underdensity might create a gravitational redshift effect, making the photons lose energy as they traveled through it, arriving colder than usual. This effect is known as the integrated Sachs-Wolf effect, but we'll come back to that later. For now, the essential question is, how likely is it that the cold spot and the supervoid are aligned just by chance? Is this a lucky overlap, a fluke of cosmic statistics, or is there a deeper connection, one that points to something we do not yet understand? This strange relationship has become one of the most hotly debated topics in cosmology. The Eridanus Supervoid challenges what we think we know about how matter clusters in the universe. It tests the limits of the standard model of cosmology. It forces us to ask whether there might be unseen physics at work, or perhaps even a glimpse into realms beyond our own universe. In upcoming segments, we'll unpack each layer of this mystery, from the nature of voids to the physics of the CMB, to the theoretical implications that ripple out from this strange alignment. But it all begins here, with a cold spot in the sky and a suspiciously empty part of space that might, just might, be too big to be real. To truly grasp the scale and strangeness of the Eridanus Supervoid, we first have to understand what exactly a supervoid is in the language of cosmology. Let's begin by zooming out, way out, to the grandest scale of all, where the universe reveals its large-scale structure. When we map the cosmos across billions of light-years, galaxies don't appear randomly scattered like grains of sugar in space. Instead, they form intricate patterns, massive filaments, dense galaxy clusters, and in between, vast regions that are remarkably empty. These empty expanses are called voids, and they're an essential feature of how the universe organizes itself. A typical void is a vast balloon-like region in space where the density of matter, both visible and dark, is significantly lower than the cosmic average. These voids aren't entirely empty, but they contain far fewer galaxies, stars, and matter than surrounding regions. Most cosmic voids range from 30 million to 150 million light-years in diameter. But supervoids go beyond even that, stretching the boundaries of what we consider possible. Supervoids are rare, enormous, underdense regions that can span hundreds of millions of light-years. They're like the Great Plains of the cosmos, deserts amid the cosmic jungle. The formation of voids is a natural consequence of how matter evolves in an expanding universe. After the Big Bang, the universe was filled with tiny fluctuations in density, regions slightly more or less dense than their surroundings. Over billions of years, gravity pulled matter from the underdense regions toward the overdense ones, leading to the growth of galaxy clusters, filaments, and superclusters. The areas that lost matter became the voids. Think of it like foam. Dense regions puff out as the empty bubbles between them grow larger. Over time, these voids become some of the most prominent structures in the cosmic web, not because they contain things, but because they don't. But even within that context, supervoids are peculiar. According to our best models of cosmology, such as the lambda cold dark matter model, large voids can form, but they should be rare, especially as large and deep as the one proposed in the Eridanus direction. What makes supervoids especially interesting is that they can affect the light that passes through them, not by blocking it, but by suddenly changing its energy. This is where they may leave imprints on the cosmic microwave background and potentially help explain anomalies like the cold spot. Still, it's important to note that even a supervoid isn't a true vacuum. It's not a hole in space. Rather, it's a region where galaxies are significantly less common, where the cosmic web stretches thin. There are still dark matter particles, still some gas, still faint galaxies drifting through. But compared to the cosmic average, the density is dramatically reduced. So when we talk about the Eridanus Supervoid, we're not suggesting that there's literally nothing there. Instead, we're suggesting that something truly extraordinary happened in that region. Something that led to a sustained underdensity across a region nearly a billion light-years across. Whether that something was a quirk of early cosmic inflation, a gravitational drain pulling matter elsewhere, or something more exotic entirely, that's the heart of the mystery. This concept of supervoids being both a normal part of the universe and yet possibly abnormal in this specific case sets the stage for why the Eridanus Supervoid is treated so differently. It's not just big, it's too big. Big enough that it may not fit comfortably in our current cosmological models. Big enough that it may even affect the energy of light itself. And big enough that it might just be the missing piece in one of the coldest mysteries in the sky.
When scientists talk about the Eridanus Supervoid, one of the first things that raises eyebrows and stretches imagination is its sheer size. This is not just another void among many. It's not a standard cosmic bubble tucked quietly between filaments. The Eridanus Supervoid is estimated to span nearly 1 billion light-years across. To put that into perspective, our entire Milky Way galaxy is about 100,000 light-years in diameter, meaning this void could theoretically hold thousands of Milky Ways side by side with room to spare. It's not just vast, it's borderline absurd in terms of cosmic proportions. This colossal estimate comes from combining observations from several galaxy surveys, including data from the 2-micron all-sky survey, 2MASS, and the Wide-Field Infrared Survey Explore, WISE. Researchers analyzing the density of galaxies in the direction of the cold spot found a noticeable dip in galactic presence, extending across hundreds of millions of light-years. The depth of this underdensity and the volume of space it covers makes it unlike any known void previously studied. The most conservative estimates suggest a diameter of around 500 to 700 million light-years. But more expansive models, especially those attempting to explain the full extent of the cold spot's temperature depression, push that figure closer to a full 1 billion light-years. That scale makes it not just large, but potentially the largest single underdense structure ever detected in the observable universe. If this estimate holds, it pushes the boundaries of what the standard colossal model says should be possible. According to the lambda cold dark matter model, such large voids are statistically very unlikely to occur. The distribution of matter on such scales should be much more uniform. While voids do exist, and even large ones are occasionally found, something of this magnitude requires serious theoretical reconsideration. It's not just big, it's too big to be real by current expectations. And yet, here it is, observed, measured, argued over, studied, by astronomers and cosmologists alike. Some claim the measurements might be overestimating its size due to projection effects or limitations in data resolution. Others argue it may not be a single void at all, but a combination of smaller voids lined up by chance. Still, the prevailing image remains, a vast ghostly canyon in the cosmic web carved into the universe on scales almost unimaginable. A void of this size also implies an incredibly long timeline for formation. It would have to have evolved over billions of years and likely required specific conditions in the early universe to become this large. If it formed naturally through gravitational clustering and cosmic expansion, then we might need to revisit how those forces played out over time. If it didn't form naturally, then the implications are far more exotic. The sheer enormity of the Eridanus Supervoid is not just a number on a scale. It's a challenge to our models, to our assumptions, and to our understanding of how the universe evolved. It forces us to confront the possibility that either we've misinterpreted the data, or that there is something fundamentally incomplete about our picture of the cosmos. The cold spot, an enigmatic, chilling anomaly in the sky, was first brought into the spotlight in the early 2000s, when cosmologists began mapping the afterglow of the Big Bang with unprecedented precision. This afterglow, known as the cosmic microwave background, is a faint but incredibly informative radiation field that fills the universe, dating back to around 380,000 years after the Big Bang. It carries within it the fingerprints of the infant universe, temperature variations, density fluctuations, and subtle clues about how matter and energy were distributed in those early moments. When the Wilkinson Microwave Anisotropy Probe, WMAP, began capturing high-resolution maps of the CMB, scientists expected to see a universe peppered with tiny temperature differences, each corresponding to regions that were slightly more or less dense in the early cosmos. And for the most part, that's exactly what they saw. But one particular region stood out. It wasn't just a little colder than average, it was dramatically colder. A large oval-shaped patch centered in the direction of the constellation Eridanus appeared roughly 70 microkelvin cooler than the surrounding areas. In the context of the CMB, where fluctuations are typically on the scale of tens of microkelvin, this was a substantial and puzzling deviation. Dubbed simply the cold spot, this region quickly became a subject of intense scrutiny. Was it a random statistical anomaly, a foreground contamination, or a sign of something cosmologically profound? At first, some suspected that local effects, perhaps emissions from the Milky Way or an instrumental artifact, might be responsible. But further analysis suggested the signal was real, persistent, and not easily explained away. Its detection wasn't a fleeting event. WMAP's findings were independently confirmed several years later by the Planck satellite, launched by the European Space Agency. Planck's instruments were more advanced than WMAP's, capable of producing higher resolution maps with better foreground subtraction. And yet, even with those improvements, the cold spot remained. Different instruments, different analysis methods, same anomaly. This consistency made it harder and harder to ignore. The cold spot isn't just cold, it's also large. It spans an area of the sky roughly 5 to 10 degrees across, depending on how one defines its boundaries. In spatial terms, that translates to hundreds of millions of light years. Its size and temperature depression are both highly unusual. The odds of such a feature appearing due to random fluctuations in a universe governed by the standard lambda cold dark matter model are extremely low. Various studies have put the probability between 1% and 0.1%. That doesn't make it impossible, but it does make it suspect. For a while, some researchers clung to the idea that this was merely a statistical outlier, a rare but meaningless blip like rolling snake eyes 3 times in a row. Others, however, began to wonder whether there might be a physical structure along the line of sight responsible for the observed cooling. Something massive, something with a gravitational power to affect the energy of the CMB photons passing through it. And that's where the Eridanus Supervoid entered the conversation. The discovery of the cold spot, followed by its verification by Planck, represents one of the most tantalizing moments in modern cosmology. Not only did it challenge our expectations of uniformity in the early universe, but it also opened the door to new and speculative ideas, from gravitational effects to multiverse collisions. It's a lingering whisper from the universe's youth that says, something strange happened here. And whatever it was, it left a cold fingerprint imprinted on the oldest light we can see. To truly understand the significance of the cold spot and why a region being slightly colder than average matters at all, we need to explore the foundation it sits upon, the cosmic microwave background, or CMB. This isn't just background radiation. It's a snapshot of the oldest light in the universe, a time capsule carrying echoes from the moment the universe became transparent, and it's one of the most important discoveries in the history of cosmology. Roughly 13.8 billion years ago, our universe began with the Big Bang, a hot, dense, chaotic fireball where energy and matter were indistinguishable, colliding and interacting constantly. For hundreds of thousands of years afterwards, the universe remained in this opaque, glowing plasma state. Photons, particles of light, couldn't travel freely. Every time they tried to move, they were immediately scattered by electrons and protons. The universe was essentially a dense fog, glowing brightly but impossible for light to traverse. But around 380,000 years after the Big Bang, a dramatic shift occurred. The temperature of the universe dropped to about 3,000 Kelvin, cool enough for electrons and protons to combine and form neutral hydrogen atoms. This event, called recombination, allowed light to decouple from matter for the first time. In that instant, the universe became transparent. The photons that were once trapped in the fog were suddenly free to travel across space, and they've been traveling ever since. These ancient photons, stretched into longer, cooler wavelengths over billions of years due to the expansion of the universe, are what we detect today as the cosmic microwave background. It now appears as a faint glow in the microwave part of the spectrum, with a temperature of just 2.7 Kelvin, barely above absolute zero. But while it's cold and invisible to our eyes, it's not uniform. It's dappled with slight temperature variations, usually just a few microkelvin in difference. These subtle fluctuations aren't noise. They're information-rich fingerprints of the early cosmos, encoding the seeds of galaxies, clusters, and voids that would later evolve into the universe we live in today. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were investigating radio noise using a large horn antenna, the CMB was the first direct evidence of the Big Bang. That faint hiss they detected turned out to be the leftover radiation from the birth of everything. Since then, missions like COBE, WEMAP, and Planck have mapped the CMB in astonishing detail, showing us that it's nearly but not perfectly uniform across the sky. The small differences, some regions slightly warmer, others slightly colder, correspond to areas of slightly different density in the early universe. These were the seeds of structure. So when we speak of the cold spot, we're referring to one of these irregularities in the CMB, but on a scale and with a temperature difference that doesn't quite fit. Most fluctuations are expected, random, and statistically predictable. But the cold spot stands out. It's too cold, too large, and too coherent. Its existence forces us to revisit our models of the early universe. Did something unusual happen in that?
And it was in the WMAP data that the cold spot first made its presence known. Sitting in the direction of the constellation Eridanus, this unusually cold region appeared far more prominent than the rest of the temperature fluctuations scattered across the sky. The anomaly was consistent across multiple WMAP releases, making it difficult to ignore or dismiss as a glitch. Even more compelling was the fact that the cold spot persisted through various data processing techniques and foreground subtraction models, meaning it wasn't easily explained away by galactic contamination or instrumental noise. But skepticism remained. Was this cold spot a real feature of the universe, or could it still be an artifact of WMAP's resolution limits or data handling? That's where the Planck satellite came in.
The Planck mission, launched by the European Space Agency in 2009, was equipped with instruments that were even more sensitive than WMAP's. It had finer angular resolution, broader frequency coverage, and the ability to separate cosmic signals from galactic foregrounds with greater accuracy. Planck's job was to take the most detailed image yet of the CMB, a high-definition portrait of the infant universe. When Planck's first results were released in 2013, one of the first questions cosmologists asked was whether the cold spot was still there. If it had disappeared in the Planck data, that would have suggested WMAP had been seeing an illusion, but it didn't disappear. On the contrary, Planck confirmed the cold spot's existence. It showed the same large cold region in the same place with remarkably similar temperature deviation. The confirmation made it clear: the cold spot is not an observational error. It's real, it's out there, and it demands an explanation. What makes both WMAP and Planck so critical is the independent confirmation they provide. These satellites had different detectors, were built by different teams, and used different calibration techniques, and yet both pointed to the same anomaly. The robustness of the cold spot across these missions has solidified its place in modern cosmology, moving it from a curiosity to a serious puzzle. Thanks to these two missions, we now have one of the most complete and consistent maps of the early universe ever created. And within those maps sits the cold spot, an enduring cosmic oddity, waiting to be understood. One of the most intriguing ideas proposed to explain the cold spot without needing to invoke new physics or alternate universes is based on a subtle and elegant mechanism in general relativity, known as the integrated Sachs-Wolf effect, or ISW effect. This phenomenon, though difficult to detect, can have a noticeable impact on the cosmic microwave background when photons pass through large-scale structures in the universe, like massive clusters or vast voids. It's a cosmic fingerprint left not by the early universe itself, but by the intervening matter that photons encounter on their 13.8 billion-year journey to us. To understand the ISW effect, we need to first imagine how light travels through the universe. When a photon from the CMB begins its journey towards us, it encounters various structures, galaxies, clusters, filaments, and also vast regions where almost nothing exists, like voids. Each of these structures has a gravitational potential well. When light enters a gravitational well, it falls in and gains energy. It becomes slightly blue-shifted. As it climbs back out, it loses that energy and becomes red-shifted again. In a perfectly static universe with no accelerating expansion, the gain and loss would cancel out completely. The photon would exit with the same energy it had when it entered. But we do not live in a static universe. Our universe is expanding, and what's more, that expansion is accelerating due to the influence of dark energy. This changing landscape means gravitational potential wells, especially those associated with large-scale structures, actually evolve over time. As the photon travels through a void or a cluster, the depth of the gravitational potential changes beneath its path. And here's where things get interesting. In the case of a supervoid like the proposed Eridanus Supervoid, the gravitational potential becomes shallower over time due to the accelerating expansion of the universe. So when a photon enters the void, it still gains a bit of energy from falling into the potential, but as it climbs back out, the well has become more shallow. It doesn't lose as much energy as it gained. That difference leaves the photon slightly red-shifted. In other words, it emerges colder than it would have been if the void weren't there. This cumulative redshifting of photons passing through large-scale underdense regions is exactly what the integrated Sachs-Wolf effect predicts. Conversely, when photons pass through overdense regions like galaxy clusters, the effect can cause them to appear slightly warmer due to the same principle in reverse. The gravitational potential well deepens as they pass through it, causing a net blue shift. But in the case of the cold spot, if there's a massive void, like the proposed Eridanus Supervoid, the integrated Sachs-Wolf effect could potentially explain the cooler temperature we observe in that patch of the CMB. However, there's a catch. The ISW effect is very weak, and even a very large void might not be enough to account for the entire depth of the cold spot. Some studies have shown that while the ISW effect from a supervoid could cause a temperature depression, the effect would only account for a fraction of the observed coldness, perhaps only 10 to 20% of it, depending on the void's exact size, shape, and depth. This means that while the ISW effect offers a partial explanation, it may not be the whole story. Still, the significance of the ISW effect is profound. It connects the ancient light of the Big Bang with the evolving structure of the modern universe. It shows that the CMB is not just a snapshot frozen in time, but a dynamic canvas, subtly altered by the fabric of space-time it passes through. If the cold spot truly is the result of an ISW effect from a massive void, then it would be a stunning demonstration of Einstein's general relativity on the largest possible scale. Yet, the debate continues. Some researchers believe that the ISW effect from the Eridanus Supervoid could explain a large part of the cold spot. Others argue the void is too shallow or too small, even at nearly 1 billion light-years wide, to have such a strong influence. Either way, the integrated Sachs-Wolf effect remains one of the most grounded and elegant explanations offered to date, a remarkable instance where the ancient past is subtly altered by the cosmic present. To test whether the cold spot might truly be linked to a vast cosmic void, scientists turn their attention to the galaxies in that part of the sky, specifically to how many of them there are, how they cluster, and how far away they are. If the Eridanus Supervoid were real, and not just a statistical illusion, there should be observable evidence of an underdensity in galaxy distribution. And so, astronomers began mining data from some of the most powerful galaxy surveys ever conducted. Two of the most critical data sets came from the 2MASS, 2-micron all-sky survey, and WISE, Wide Field Infrared Explorer missions. These surveys mapped the positions and brightness of millions of galaxies across the entire sky, primarily in the infrared spectrum, which is especially good for peering through dust and detecting older, redder galaxies. By combining these surveys, researchers could build a three-dimensional map of galaxy distribution, not just where galaxies appear on the sky, but how far away they are from us, using redshift measurements. When the galaxy distribution in the direction of the Eridanus constellation was analyzed, a clear pattern emerged. There was a significant dip in the number of galaxies observed over a large volume of space. In simpler terms, a large portion of the sky in that direction had far fewer galaxies than would be expected in a typical region of the universe. This underdensity spanned a wide range of redshifts, corresponding to hundreds of millions of light-years of distance, reinforcing the idea that we're not just looking at a small gap in one layer of the universe, but rather a broad, volumetric emptiness. What's even more compelling is how gradual the underdensity appears to be. Instead of being an abrupt hole, the survey showed a gentle thinning of galaxies across a wide area, as if the cosmic web were fraying in that direction. This pattern is consistent with what we would expect from a supervoid, rather than from several small voids or random variations. In particular, a 2015 study by Istvan Sapudi and colleagues estimated that the observed underdensity extends out to a redshift of about z equals 0.15 to 0.25, which corresponds to roughly 1 to 3 billion light-years away. The surveys also revealed that the void appears to be centered close to the cold spot's location, providing one of the strongest pieces of observational evidence that these two phenomena may be linked. It's not just that the region is underdense, it's that the emptiest part of this underdense region sits directly in the path of the cold spot, raising the question, is this alignment a rare fluke, or is it pointing to a deeper connection? But interpreting galaxy survey data is far from straightforward. Galaxies are not evenly distributed to begin with, and local features like foreground stars, galactic dust, and observational biases can all skew the results. To account for this, astronomers compare the galaxy counts in Eridanus with control fields, similarly sized regions elsewhere in the sky, to see if the dip is truly unique. Again and again, the Eridanus region shows a statistically significant deficit in galaxies. Still, some researchers argue that while the region is indeed underdense, the depth of the void, meaning how empty it truly is, may be overestimated due to limitations in the data or assumptions made during analysis.
There's also debate about whether the underdensity is caused by a single enormous void or by multiple smaller voids overlapping along the line of sight, creating the illusion of one giant structure. This distinction.
While the term supervoid might conjure images of a vast cosmic emptiness, a giant hole in space where absolutely nothing exists, the reality is subtler and in many ways more fascinating. The Eridanus Supervoid is not completely empty. It's not a vacuum in the purest sense. Instead, it's what cosmologists call a significantly underdense region, a part of the universe where the number of galaxies, clusters, and even dark matter is far lower than average, but not zero. In cosmological terms, underdense means that the density contrast, the measure of how much matter exists in one region compared to the average, is negative. If the average matter density in the universe is normalized to 1, then typical voids might have a density of around 0.2 to 0.4. Supervoids, like the one proposed in Eridanus, might have densities closer to 0.1 or even lower. That's a dramatic drop, but still far from nothingness. There are still galaxies drifting through, still stars forming here and there, still gas and dark matter present, just far, far less of it than usual. This underdensity is crucial to the void's potential influence on the cosmic microwave background. For a void to affect the temperature of the CMB via the integrated Sachs-Wolf effect, it doesn't need to be completely empty. It just needs to lack enough mass to cause a slight difference in gravitational potential over time. The Eridanus Supervoid, with its immense scale and reduced matter density, meets that requirement. It may not be a hole, but it is a gravitational low-pressure zone, so to speak, a region where light traveling from the early universe is subtly redshifted as it passes through. Moreover, it's important to remember that the cosmic web, the large-scale structure of the universe, is composed of interconnected filaments and nodes surrounded by vast voids. These voids are expected features of structure formation, resulting from gravitational collapse drawing matter into denser regions and leaving underdense areas behind. What makes the Eridanus region unusual isn't that it's underdense, it's how underdense it is, and over such an extensive volume. Astronomers looking at galaxy surveys in this region still detect galaxies, but their number density drops off considerably compared to control regions elsewhere in the sky. Even within the void, there are likely smaller-scale structures, wisps of gas, small galaxy groups, and isolated dark matter clumps. In some ways, these regions may resemble the rural outskirts of a vast urban galaxy network, lonely, dimly lit places far from the bustle of galactic cities. Clarifying this point is essential when interpreting the void's potential influence on the CMB. If people imagine the supervoid as a literal hole in the fabric of space, they may overestimate its gravitational influence or expect it to be more visible. But the influence of a supervoid lies not in its absolute emptiness, but in its relative absence of matter compared to what's expected. It's the cumulative effect of this deficit across a staggering scale that might produce a subtle but detectable fingerprint on the ancient light from the Big Bang. In the case of the Eridanus Supervoid, that fingerprint is potentially the cold spot. Whether or not the void is solely responsible for it, understanding that we're not dealing with a void in the absolute sense, but rather a cosmic light fog instead of a deep black pit, helps ground our expectations. The universe doesn't create perfect vacuums on these scales, but it does carve out quiet, dim, underpopulated stretches that span hundreds of millions of light years. These are the cosmic deserts. Not barren wastelands, but hauntingly sparse landscapes where galaxies are few and far between, and where the universe whispers rather than shouts. The apparent alignment between the cold spot and the Eridanus Supervoid raises one of the most critical and controversial questions in modern cosmology. Are these two phenomena truly connected, or is their positioning on the sky just a cosmic coincidence? At first glance, the correlation seems too precise to ignore. The cold spot, a large and unusually cold region in the cosmic microwave background, is centered almost exactly in the same direction as the observed underdensity of galaxies in the Eridanus constellation. Given the scale of both, the cold spot spanning roughly 5 to 10 degrees of sky and the Eridanus Supervoid being estimated to be nearly 1 billion light-years across, it's tempting to conclude that one must be causing the other. That's certainly what some researchers believe.
If a photon from the CMB passes through a massive supervoid like Eridanus, then, as we've discussed, it could lose a tiny bit of energy due to the integrated Sachs-Wolf effect and show up slightly colder than expected. Simple, elegant, and plausible. But not everyone is convinced. And the reason lies in the numbers. Multiple studies have modeled the expected ISW effect produced by a void with the dimensions and depth of the Eridanus Supervoid. What they found is surprising. The void does produce a temperature dip in the CMB, yes, but it doesn't go nearly far enough. Most models suggest the ISW contribution would only explain about 10 to 20% of the cold spot's temperature deviation. That's a meaningful amount, but it falls far short of explaining the entire anomaly. If the cold spot is around 70 microkelvin colder than average, then the void might only account for a 10 to 15 microkelvin drop. This shortfall opens the door to doubt. If the void isn't responsible for the majority of the cold spot's coldness, then what is? Could there be another deeper structure we haven't detected yet? Is there a flaw in our assumptions about the void's depth or geometry? Or, more uncomfortably, is the cold spot an entirely separate phenomenon, and the supervoid's alignment just an unfortunate trick of cosmic perspective? The universe is large, unimaginably large, and it's filled with structure. Even in a statistically random distribution of galaxies and temperature fluctuations, chance alignments can and do occur. In fact, some studies have attempted to calculate how likely such an alignment is under the standard lambda cold dark matter model. Depending on the parameters used, the odds of a void of Eridanus's apparent size aligning with a cold spot of this temperature can range from 1 in 50 to 1 in several thousand. Rare, yes, but not impossible. In a universe with billions of observable regions, rare events happen all the time. This is the heart of the debate. Is this one of those rare flukes, or is it a meaningful connection? If it's a fluke, then we may be looking at an over-interpretation, a case of the human mind's instinct to find patterns where none exist. But if it's real, then we're staring at an empirical clue that could expose a new chapter in cosmological history, perhaps a hint at exotic physics, or even hints of the multiverse. Another factor complicating this question is observational uncertainty. The Eridanus Supervoid is not a sharply defined object with an obvious edge. Its boundaries are fuzzy, and its depth is inferred from statistical surveys that have limitations in resolution, completeness, and redshift accuracy. Meanwhile, the cold spot, while clearly present, also depends on how you define its borders and which temperature thresholds you choose. These uncertainties create room for both interpretations, one that insists the connection is real but incomplete, and another that suggests the entire matchup is a red herring. To resolve the question, scientists are pushing for deeper, higher-resolution galaxy surveys in the cold spot's direction, ones that can map the void's structure with more detail and clarity. They're also studying the properties of galaxies within and around the void to see if their behavior differs in ways that could support a physical link. But until those datasets are available, and until the models improve, we're left in an uneasy position. Maybe the cold spot and the Eridanus Supervoid are two sides of the same coin, connected by a gravitational thread we're only beginning to understand. Or maybe they're just neighbors in the sky, close but cosmologically unrelated. The answer, whatever it turns out to be, will either deepen our understanding of cosmic structure or remind us just how skilled the universe is at fooling our eyes. Under the lens of our current understanding of the universe, most notably through the lambda cold dark matter model, the existence of something as enormous as the Eridanus Supervoid presents a statistical oddity. While voids are expected and well-modeled feature of cosmic evolution, a void on the scale of nearly 1 billion light-years across, with a depth great enough to noticeably impact the cosmic microwave background, sits uncomfortably on the far edge of what our best models say should exist. In fact, some argue it may not even belong there at all. Let's start with what lambda cold dark matter model predicts. This model, the prevailing cosmological framework, describes a universe composed primarily of cold dark matter and dark energy, expanding under the influence of general relativity. It has proven remarkably successful in explaining everything from the formation of galaxies to the distribution of galaxy clusters and voids, but like any model, it produces statistical expectations.
Simulations based on lambda cold dark matter models, such as the Millennium simulation and more recent high-resolution large-scale structure simulations, generate cosmic web maps with voids of varying sizes. Most of these voids, the majority in fact, fall into a fairly narrow range of dimensions, typically 20 to 150 million light-years in diameter. Occasionally larger ones do form, perhaps in the range of 200 to 300 million light-years, but these are considered relatively rare. Now compare that to the Eridanus Supervoid, which some models place at 900 to a billion light-years wide. This isn't just slightly larger, it's orders of magnitude larger. Simulations under lambda cold dark matter model generally do not produce voids of that scale. The statistical likelihood of such a structure forming naturally is extremely low. Depending on the assumptions used, less than 1 in 100,000 simulations may produce something comparable. That makes the Eridanus Supervoid, if confirmed, a serious outlier, the cosmological equivalent of flipping a coin 1,000 times and getting heads every time. And it's not just the size that poses a problem, it's also the depth. A massive region that is only slightly underdense might not be that troubling. But the Eridanus Supervoid,
if the Eridanus Supervoid falls within those statistical expectations, even if barely, then it may simply be an example of cosmic randomness at work. A fluke, a low probability event, but not an impossible one. Some researchers have likened it to the idea of rolling a pair of dice and getting snake eyes. Rare, yes, but given enough rolls, it happens. And in a universe as large as ours, with hundreds of billions of observable regions, even very rare voids will occasionally appear somewhere. But is that what's happening here? The cold spot associated with the supervoid is itself already a low probability event, and the odds of it aligning with such an unusually large underdense region only compound the rarity. When taken together, some analyses suggest the joint probability of both the cold spot and the Eridanus Supervoid occurring and aligning by chance may be as low as 0.1% or even less. That doesn't cross the threshold into impossibility, but it does invite scrutiny. In science, when extremely low probability events occur, especially ones that line up with unexplained anomalies, the result is not always to dismiss them, but to ask, could this be pointing to something more fundamental? That's where the possibility of new physics enters the conversation. Some theorists suggest that the void, if it's real and fully as large and deep as observations imply, could be a relic of non-Gaussian initial conditions. In other words, perhaps the early universe didn't start out as smooth and predictable as we've assumed. Maybe certain regions experienced primordial fluctuations that were enhanced, leading to extreme underdensities like Eridanus. This would challenge a key pillar of standard inflationary theory and demand a revision of the initial conditions assumed in cosmological models. Others speculate that dark energy might behave differently on the scale of voids than it does on the scale of galaxies or galaxy clusters. This could mean the physics governing expansion isn't uniform across all regions. Perhaps there's a hidden complexity in the vacuum energy of space that affects the growth of large voids. If true, it might explain how such a massive underdensity formed and evolved without requiring new particles or exotic physics. Then there are even more radical possibilities, including the idea that the cold spot, and possibly the supervoid itself, are signs of a bubble collision with another universe, or that the large-scale structure of the cosmos is being influenced by physics from higher dimensions or multiversal interactions. These ideas lie far beyond the standard model and remain speculative. But the point is that the presence of anomalies like Eridanus creates the conditions in which such bold theories are entertained seriously, at least long enough to explore their mathematical viability. At the same time, science demands caution. Extraordinary claims require extraordinary evidence. It's entirely possible that the void size has been overestimated due to observational biases, foreground noise, or redshift projection errors. It's also possible that the cold spot, while rare, is a statistical mirage, a product of the random distribution of early universe fluctuations that happens to look more significant than it is. To distinguish between these two possibilities, chance or change, scientists need more data. Larger, deeper galaxy surveys, better redshift resolution, and more refined CMB analyses will be key.
Simulations that incorporate even rarer initial conditions or non-Gaussianities are being developed to test how often voids like Eridanus should appear if the assumptions of standard cosmology are bent just slightly. In the end, the question of whether this void is a cosmic fluke or a clue toward new physics remains unresolved. But it stands as a perfect example of how science progresses, not through certainty, but through persistent questioning of the unexpected. Whether the Eridanus Supervoid is a statistical ghost or a physical revelation, its presence ensures that we keep pushing the boundaries of what we think we know, and that, in itself, is evidence of a healthy, curious universe of minds. Among the most daring and mind-stretching hypotheses proposed to explain the cold spot, and perhaps indirectly the Eridanus Supervoid, is the idea that this frigid patch in the cosmic microwave background might be the bruise left behind from a collision with a parallel universe. As strange as it sounds, this is not just wild speculation. It's a concept that emerges naturally from certain cosmological models, especially those involving eternal inflation and the multiverse. To understand this hypothesis, we first need to revisit the theory of cosmic inflation. According to inflationary theory, our universe underwent a period of rapid exponential expansion a tiny fraction of a second after the Big Bang. This process smoothed out the fabric of spacetime and seeded the tiny fluctuations that would later grow into galaxies and large-scale structures. But many versions of inflation, particularly eternal inflation, don't stop with just one universe. In eternal inflation doesn't end everywhere at once. Instead, it continues indefinitely in different regions of space. Occasionally, a bubble of non-inflating space, a pocket universe, will nucleate, like a bubble forming in boiling water. Each of these bubbles is a separate universe, with potentially different physical constants, laws, and histories. Our universe would be just one such bubble in a vast, possibly infinite multiverse. Now imagine what might happen if two of these bubbles, two universes, collided. The idea, proposed by researchers including Anthony Aguirre and Matthew Johnson, is that such a collision would leave a disk-like imprint in the cosmic microwave background of the surviving universe, a region where the temperature is slightly different from the rest due to the energy and momentum exchanged during the contact. If this happened early enough, while the CMB was still being formed, the signature could still be visible today. Enter the cold spot. The cold spot, as observed by both Waymap and Planck, is unusually large and significantly colder than the surrounding regions, far more so than random Gaussian fluctuations would predict. And while the Eridanus Supervoid may account for some of the coldness through the integrated Sachs-Wolf effect, it doesn't explain the full magnitude of the anomaly. This gap in explanation is what opened the door to more exotic ideas, like the parallel universe collision hypothesis. If the cold spot were indeed caused by a bubble collision, it would explain several features. The shape of the cold spot is roughly circular, and its temperature profile has a central dip with a surrounding warmer ring, a pattern that could match the energy dissipation from such a cosmic impact. Simulations of bubble collisions suggest that the resulting disk could span several degrees of the sky and have a temperature depression consistent with the cold spot's characteristics. Critically, this explanation would not require an enormous void in the same direction. The Eridanus Supervoid, in this view, might be unrelated, or perhaps even a secondary effect, where the altered spacetime geometry from the bubble collision affected matter distribution in that direction, creating a void-like structure as a byproduct. But let's be clear, this idea remains highly speculative. There is no direct evidence for a multiverse, let alone a bubble collision. Moreover, the probability of such a collision happening within our observable universe and leaving a trace visible in the CMB is considered extremely low under many inflationary models. Most of the time, if universes collide, the resulting energy would be catastrophic, potentially obliterating structures and leaving the universe inhabitable. The scenario where a collision produces a mild temperature anomaly without destroying the fabric of our universe requires very specific and narrow conditions. And yet, it hasn't been ruled out. In fact, some researchers have tried to systematically search the CMB for similar anomalies, looking for circular patterns or disks that could indicate other collisions. So far, the cold spot remains the most prominent candidate. It is the only region on the sky where a case can be made that both the shape and the temperature deviation align, even loosely, with the theoretical predictions of a multiverse collision. If true, the implications would be staggering. The cold spot wouldn't just be a patch of cold light, It would be a window into a larger cosmic landscape, a hint that our universe is not alone and that others may have brushed against ours long ago. We would be living in a multiverse, where our observable universe is just one bubble in a frothing sea of realities, each possibly governed by different physics, different time flows, and different histories. But extraordinary claims demand extraordinary evidence. Until we find more such cold spots, or better theoretical and observational confirmation, the multiverse explanation must remain an intriguing possibility, not a conclusion. Still, the fact that such a hypothesis even competes for consideration is a testament to the cold spot's power, a small region of cold light that might carry the echo of another universe crashing into our own. Another fascinating possibility, one that remains within the bounds of physical cosmology but nudges us toward its most speculative edges, is the idea that the Eridanus Supervoid might not be a product of late-time structure formation at all, but a primordial imprint, a feature seeded during the universe's earliest moments, specifically during cosmic inflation. If this is true, then it would mean the void is not a coincidence of gravitational dynamics or galactic migration, but a fossil remnant of the universe's very birth. To appreciate this, we need to return to the briefest and most explosive era in the universe's history, the inflationary epoch. According to inflation theory, just a fraction of a second after the Big Bang, the universe underwent a dramatic and exponential expansion, ballooning from subatomic scales to macroscopic sizes almost instantly. This rapid expansion smoothed out the fabric of spacetime and seeded the tiny fluctuations that would later grow into galaxies and large-scale structures. But while inflation is generally thought to produce nearly Gaussian and statistically homogeneous fluctuations, meaning that the early universe was nearly uniform, with only minor variations, there is room for exceptions. Some versions of inflationary theory allow for non-Gaussian perturbations, rare but much larger than average deviations from the mean. These rare fluctuations could lead to unusually overdense or underdense regions, and if a sufficiently large underdensity was born during inflation, it could, in theory, evolve into a supervoid like the one we see in Eridanus. In this view, the Eridanus Supervoid.
Mathematically, voids can be modeled using tools like the Zeldovich approximation and n-body simulations, which track the movement of matter under gravity over cosmic time. These simulations reproduce a universe that looks strikingly like our own, with thousands of voids filling the space between structures, each shaped by surrounding forces and often interconnected, forming a network of emptiness. Interestingly, voids also expand faster than the rest of the universe. In a dense region, gravity can slow down expansion, or even cause localized collapse, as with galaxy clusters. But in a void, where gravity is weaker, the space between particles stretches more freely. This means that voids become larger over time, not because matter is being pushed outward, but because there's so little gravitational resistance in those regions to begin with. This is why by the present epoch, nearly 14 billion years after the Big Bang, voids occupy a majority of the universe's volume. Though they contain only a small fraction of its matter, they dominate the universe in space. They're not just the gaps between things, they're a defining feature of the cosmic structure. So when cosmologists study voids, they're not just studying absence, they're studying the geometry of the universe itself. And this makes the Eridanus Supervoid such a puzzle. If it formed like typical voids, it should fit within the size limits and density profiles we've come to expect. But it doesn't. It's too big, too smooth, too aligned with an anomaly in the CMB, and perhaps most unsettling of all, too quiet in a place where the universe is usually full of structure. That's what makes it exceptional. The Eridanus Supervoid isn't strange because voids are rare. It's strange because this one refuses to behave like the rest. When we place the Eridanus Supervoid side by side with the thousands of other known voids in the cosmic web, the differences become immediately striking, not just in scale, but in structure, coherence, and potential implications for cosmological models. While normal voids are common, well understood, and expected features of the universe's architecture, Eridanus stands out like a canyon in a landscape of hills. Not impossible, perhaps, but certainly rare and suspiciously deep. Typical cosmic voids, as observed in large-scale galaxy surveys, tend to range from about 20 million to 100 million light-years across. Even the largest voids cataloged in the Sloan Digital Sky Survey, SDSS, or the 2-mass redshift survey, rarely exceed 200 million light-years in diameter. These voids are often irregular in shape, interwoven with surrounding filaments and sheets of galaxies, and tend to be moderately underdense, not entirely empty. On average, a typical void might have 15 to 30% less matter than the cosmic mean, depending on how it's defined and measured. Now, contrast this with the Eridanus Supervoid. Initial estimates based on data from the WISE 2-mass survey, followed by follow-up analysis using Planck and other datasets, suggest that the Eridanus Supervoid may span up to 900 million to 1 billion light-years across in co-moving scale. That's 5 to 10 times larger than a standard void, a truly gargantuan cavity in the universe's structure. Even more staggering is its angular diameter, which spans roughly 5 to 10 degrees of the sky, a breadth that covers a significant portion of the southern celestial hemisphere, aligning almost exactly with the cold spot in the CMB. In terms of underdensity, estimates vary, but several studies suggest a matter deficit of 20 to 30%, possibly even greater if the void is modeled as a stacked series of subvoids. Although this underdensity isn't the deepest ever observed, its enormous spatial extent makes it unusually influential. Most voids, even if deep, don't span nearly 1 billion light-years. Eridanus manages to be both deep and wide, and that combination is what pushes it into anomalous territory. Structurally, the Eridanus Supervoid also differs from standard voids. Most cosmic voids are irregular, shaped by surrounding structures, gravitational gradients, and local expansion patterns. But Eridanus appears more coherent, a smooth, roughly spherical or ellipsoidal region with relatively consistent underdensity throughout. It doesn't have a ragged boundary or multiple cores of emptiness. Instead, it gives the appearance of a single monolithic depression in the cosmic fabric, although some researchers argue it may be a superposition of smaller voids aligned by chance. And then there's its location, perfectly aligned with the cold spot. Most voids are scattered randomly across the sky, their effects on background radiation minor or negligible, but the Eridanus Supervoid lies in a position of cosmic coincidence, directly in the line of sight of one of the most significant anomalies in the CMB. That alignment, combined with its unusual size and structure, is what elevates Eridanus from an interesting feature to a possible cosmological challenge. It's worth noting that several other large voids have been found, such as the Boötes void, which spans around 300 million light-years, and the local void, a large underdensity near our own galaxy. But even these pale in comparison. The Eridanus Supervoid, if confirmed in its current form, would be among the largest single structures, or anti-structures, ever detected in the observable universe. This raises a fundamental question. Should we consider it an outlier in a well-understood distribution of voids, or does it hint at something deeper, perhaps a flaw in our assumptions, a new kind of structure, or an imprint from the early universe that survived inflation and expansion intact? Either way, its sheer size, relatively smooth interior, and precise angular alignment with the cold spot make the Eridanus Supervoid an object of intense interest. Not just a void, but potentially the void that breaks the rulebook. While some studies paint the Eridanus Supervoid as a vast, singular underdensity nearly 1 billion light-years across, others propose a more nuanced picture, that what we perceive as one enormous void may actually be a composite structure formed by the overlap and alignment of several smaller voids stacked along our line of sight. This theory attempts to reconcile the unusual scale and profile of the void with the constraints of standard cosmological models, which struggle to accommodate such an enormous emptiness as a single coherent structure. The idea is rooted in observational techniques. When astronomers survey galaxies at great distances, particularly using photometric redshifts, which are faster but less precise than spectroscopic methods, the fine-grained depth information is often smeared.
This blurring makes it difficult to distinguish whether we're seeing one deep and extended void or several smaller voids at slightly different redshifts, one behind another. If those smaller voids just so happen to be aligned in the direction of the cold spot, they could mimic the signal of a single supervoid, an illusion created by perspective and limited resolution. Simulations and survey analyses support this possibility. Cosmic voids are not evenly spaced, nor are they isolated. They tend to cluster in low-density regions and can form void complexes, groups of voids nearby with overlapping boundaries. In such environments, the collective gravitational effects and underdensities of multiple voids can produce a cumulative impact on both matter distribution and background radiation. In the case of the Eridanus region, some researchers have analyzed galaxy counts across narrow redshift bands and found indications of multiple dips in density rather than one broad, uniform underdensity. These dips suggest the presence of several discrete voids, each perhaps 100 to 200 million light-years across, rather than one monolithic void nearly a billion light-years wide. This model of stacked or nested voids offers several advantages. First, it aligns more naturally with predictions from the lambda cold dark matter model, which does produce large voids, but rarely of the extreme size proposed for Eridanus. A series of smaller voids, even if collectively vast, would fall within the statistical expectations of standard cosmology. Second, the combination of these voids could still have a measurable effect on the cosmic microwave background, contributing to the observed cold region via the integrated Sachs-Wolf effect, though likely not fully accounting for its intensity. There's also a morphological implication. If Eridanus is not a smooth spherical depression, but a layered structure with gaps and fluctuations, it might explain the non-uniformity of the cold spot's temperature gradient, its warm outer ring, for example, and the slightly asymmetrical shape. A multi-void arrangement would naturally create a more complex lensing and gravitational environment than a single void, affecting not just the CMB photons, but also the distribution and motion of galaxies in that direction. Still, challenges remain. Even with multiple smaller voids, the combined depth and width of the apparent underdensity remains extreme. Critics argue that while a stacked void model might reduce the statistical tension with lambda cold dark matter model, it doesn't entirely eliminate it. The odds of having so many voids aligned just so, along a line of sight that also coincides with the cold spot, might still be low enough to raise eyebrows. It could be a coincidence, yes, but it could also be a signpost pointing to an early universe event that affected structure formation on a grand scale. In the end, the stacked void model serves as a kind of cosmic compromise, an attempt to preserve the established model of the universe while still addressing the unusual features.
But here's the catch. If dark energy can stretch voids this dramatically, then why don't we see more voids like Eridanus? Why isn't the sky full of such vast emptiness? That question remains unsettled, and it's one reason why the Eridanus Supervoid, for all its potential explanation by conventional physics, still feels like an anomaly, a structure whose size, smoothness, and location continue to provoke both curiosity and caution. Still, it's hard to ignore the elegance of the idea. A vast, underdense region, subtly stretched by the repulsive pressure of dark energy, quietly expanding over billions of years, not in defiance of cosmology, but in full, majestic cooperation with it. Despite the intrigue and attention the Eridanus Supervoid has garnered, not all scientists are convinced of its existence. In fact, a significant body of work casts doubt on the idea that a single, vast, coherent supervoid exists at all in the direction of the cold spot. The critiques stem from multiple angles: observational limitations, statistical uncertainties, data inconsistencies, and alternative interpretations, all of which add layers of complexity to an already mysterious region of the universe. One of the main criticisms lies in the resolution and depth of galaxy surveys used to detect the underdensity. Many of the early claims for the Eridanus Supervoid's existence came from surveys like WISE 2MASS, which combine infrared sky data with photometric redshift estimates to infer galaxy distances. But photometric redshifts, unlike spectroscopic ones, are inherently imprecise. Their uncertainties can smear out structures in redshift space, making a series of smaller voids appear like one large, continuous underdensity. Critics argue that without high-resolution, spectroscopic redshift confirmation, the so-called supervoid may be nothing more than an observational artifact, an illusion caused by limited data granularity. Another layer of skepticism arises from survey completeness. The galaxy counts used to infer the void rely on surveys that can be biased by observational limitations, such as galactic dust, star crowding in the Milky Way's plane, and sky coverage irregularities. In the region near the cold spot, the galactic foreground is especially problematic. Some researchers have raised the possibility that what looks like a drop in galaxy density might actually be due to dust extinction or stellar contamination, which can obscure background galaxies and mimic a void-like signal. Moreover, there are statistical uncertainties to consider. The universe is full of random fluctuations in temperature, in galaxy density, in clustering patterns. Some researchers argue that the observed underdensity is not statistically significant enough to warrant the label of a supervoid. While it may be a slightly emptier than average patch of sky, its deviation from the mean could fall within the expected cosmic variance, the natural range of fluctuation allowed in the standard cosmological model. From this perspective, the Eridanus region may simply be a statistical fluctuation, nothing more than cosmic coincidence. Compounding the problem is the inconsistency across different datasets. Some studies confirm a moderate underdensity in the direction of the cold spot, while others do not see anything unusual. Depending on the galaxy sample, redshift slicing method, and survey parameters, the void's depth, size, and even presence can shift dramatically. This inconsistency has led several researchers to caution against definitive claims about the void's structure, without more robust, cross-validated data. Then there's the question of the cold spot itself. If the supervoid is meant to explain the cold spot via the integrated Sachs-Wolf effect, it must be deep and extended enough to create a temperature decrement in the cosmic microwave background. But simulations and theoretical modeling suggest that even the largest realistic voids cannot produce a cold spot of the observed amplitude. In other words, even if the void exists, it might not be responsible for the cold spot, which raises further doubts about the physical significance of either feature. A deeper philosophical criticism concerns the narrative temptation to find meaning in coincidental alignments. Human cognition is wired to seek patterns, and in a vast, complex dataset like the universe, it's easy to draw connections that aren't truly causal. Critics argue that the supposed alignment between the cold spot and the Eridanus supervoid may simply be a case of confirmation bias, where attention is focused on that region because it's already anomalous in one way, prompting further scrutiny that reinforces a perceived anomaly. Ultimately, the existence of the Eridanus supervoid remains an open question, one balanced precariously between suggestive evidence and serious doubt. The criticisms don't disprove the void's reality outright, but they do caution against overinterpretation. In the absence of definitive data, particularly from high-resolution, deep-field spectroscopic surveys, the void remains a possibility, not a certainty. The cosmos is filled with shadows, both literal and interpretive. And in the case of Eridanus, what we're looking at might not be a vast emptiness, but the limits of our own observational reach, a kind of cosmic mirage shaped by incomplete data, noisy maps, and the fundamental randomness of the universe itself. As with many tantalizing discoveries in cosmology, the question looms: what if the Eridanus supervoid is not a grand structure carved into the fabric of space, but simply a product of our own limitations? Could it be an observational error, a misinterpretation, or an artifact born of incomplete data, biased assumptions, and statistical noise? These possibilities are not only worth considering, they are essential to weigh before accepting any bold claim that might challenge the foundations of our cosmological model. The most basic form of observational error comes from the way light travels through space and how it is interpreted when it reaches us. When we observe distant galaxies, we're looking through layers of interference, intervening dust, stellar foregrounds, instrumental noise, and survey limitations.
especially in the region of the sky containing the cold spot. Milky Way dust and stellar contamination can obscure background galaxies, and even the most careful dust corrections may not fully recover the true density of distant background sources. Another issue lies in the nature of the galaxy surveys used to identify the void. Many of the early void analyses in the Eridanus region rely heavily on photometric redshifts, which are derived from broad color filters rather than precise spectral lines. While photometric redshifts can offer coverage across vast sky areas, they come with significant uncertainties, often on the order of delta Z equals 0.03 to 0.05. This uncertainty in redshift translates into blurred distance measurements, making it difficult to determine if galaxies are clustered or spread out, and whether a void exists at a specific depth or not. This blurring effect can result in what appears to be a smooth, extended underdensity, in other words, a supervoid, even when no such coherent structure exists. If multiple smaller voids lie at different distances and photometric uncertainties smear them into one single region, they may create the illusion of continuity where none exists. The outcome? What looks like one big void might just be observational stitching. There's also the possibility of survey homogeneities, inconsistencies in how galaxies are detected across different parts of the sky. For example, if a particular region has slightly less complete data, perhaps due to lower telescope sensitivity or atmospheric distortion in ground-based observations, it might artificially appear less populated with galaxies. Even satellite data is not immune. Differences in calibration, exposure time, and detection thresholds can introduce subtle biases in the final maps, which may be mistaken for real cosmic features. Additionally, the process of data selection and smoothing can introduce interpretation errors. Many void detection algorithms rely on spatial smoothing to reduce noise and highlight large-scale trends. But smoothing, if not carefully constrained, can cause spurious voids to appear, especially when applied to sparsely sampled or uneven data. In the case of Eridanus, if the underlying galaxy distribution was already patchy or incomplete, smoothing it could artificially create the impression of a vast emptiness where there are simply regions of lower data density. Critically, the confirmation bias of researchers, a cognitive tendency to seek patterns that support a pre-existing hypothesis, must also be considered. Once the cold spot was identified in the CMB, attention was inevitably drawn to that region of the sky. It became a target for anomaly hunting. Any underdensity found in that direction was suddenly more compelling than one found elsewhere, even if statistically similar. This doesn't mean the void isn't real, but it means we must ask, would we be giving it as much attention if it weren't aligned with the cold spot? Probably not. And finally, there's the cautionary tale of past cosmic misinterpretations. History is full of features that appeared anomalous at first, but faded with improved data. For example, the Great Wall of Galaxies, once thought to be a structure challenging the cosmological principle, was later explained as part of the natural cosmic web. Similarly, earlier claims of vast voids or unusual alignments have often turned out to be data processing artifacts later corrected or downplayed. In the end, skepticism is not a rejection of the Eridanus Supervoid. It's a necessary filter through which all scientific claims must pass. The possibility that we're looking at an observational artifact is not an indictment of bad science, but a recognition of just how difficult it is to read the universe's signature through the cloudy lens of limited data and noisy skies. Until deeper high-resolution spectroscopic surveys map the region in finer detail, we must live with this uncertainty. The supervoid may be a real structure, or it may be the echo of our own instrumentation, a shadow cast not by cosmic emptiness, but by
At its core, cosmic variance is the recognition that even in a perfectly understood and statistically predictable universe, some fluctuations, especially on very large scales, will happen simply due to random chance. It's the cosmological equivalent of rolling a die. You may expect the average result to be 3.5, but if you roll only once, you might get a 1 or a 6. The universe, having evolved from a sea of quantum fluctuations magnified by inflation, is one single roll, and it may just be a particularly weird one. This concept is especially relevant when looking at the largest angular scales of the cosmic microwave background, the domain of the cold spot and the axis of evil. The number of independent data points, or modes, at these scales is small, very small. For the quadrupole and octupole, we're talking about just a few spherical harmonics that span the entire sky. Because of this, there is inherent statistical noise in how those modes appear. Even in a universe that follows the lambda cold dark matter model perfectly, the largest scale fluctuations will exhibit variation, and sometimes they may look downright strange. The cold spot might then just be a statistical outlier, a low probability but perfectly possible deviation caused by cosmic variance. In fact, several studies have attempted to quantify the likelihood of such a feature arising naturally. Depending on the definition and the statistical test used, the cold spot's occurrence in simulations ranges from being a 1 in 50 to 1 in 1,000 event. That's rare, but not impossible, especially when you consider the thousands of patches of sky you could examine. The problem becomes more complicated when multiple anomalies are considered. If you only test for one strange feature, the significance of a rare event is easier to evaluate. But if you search across the entire CMB map for any deviation from the norm, the chances of finding something odd increase dramatically. This is where cosmic variance blurs into what's called the look elsewhere effect. The more you look, the more likely you are to find something seemingly improbable, even if it's just noise in a single realization. Even with that in mind, some cosmologists argue that the cold spot, and by extension any apparent void aligned with it, doesn't necessarily require exotic physics or a breakdown of the lambda cold dark matter model. It could simply be a perfectly normal result of random initial conditions, stretched across the cosmos and observed from our specific vantage point. In this view, anomalies like Eridanus or the axis of evil might be red herrings, echoes of randomness mistaken for meaningful structure. Yet this explanation, while powerful, is also deeply unsatisfying to many. It offers no mechanism, no new insight, no physical cause, just a shrug of the shoulders and a reminder that the universe might be weirder than the average, but not broken. It's not wrong, but it's difficult to prove, and harder still to accept when multiple peculiar features all line up in one part of the sky. Ultimately, cosmic variance places a kind of statistical ceiling on our ability to make definitive claims about the largest structures and anomalies in the universe. It tells us that some mysteries may remain just that, not because they are beyond physics, but because they are part of the noise baked into the very fabric of cosmic history. In the case of the cold spot and the Eridanus Supervoid, cosmic variance remains the simplest possible explanation, a whisper from chance, not a shout from a deeper truth. But if more anomalies continue to emerge in the same region of space, or if future data reveals patterns that go beyond what random chance can comfortably explain, then perhaps the dice weren't rolled fairly after all. The vastness of the Eridanus Supervoid isn't just a curiosity in terms of size or structure. It has real consequences for how light travels through the cosmos. One of the most profound ways this underdensity could influence our observations is through its impact on gravitational lensing, the bending and distortion of light as it travels across the warped fabric of spacetime. While gravitational lensing is typically associated with massive structures like galaxy clusters, even voids, by virtue of their lack of mass, can subtly bend the paths of photons, leading to measurable effects. In areas of space where mass is abundant, such as in galactic filaments or clusters, light is pulled inward by gravity, causing converging lensing. This can magnify or distort the images of background galaxies, creating arcs, shear patterns, and lensing caustics. But a void, like Eridanus, does the opposite. It acts as a kind of diverging lens. Light passing through a large, underdense region can be slightly defocused, resulting in what is known as weak lensing demagnification.
The photons that make up the cosmic microwave background are especially vulnerable to such effects, given that they have been traveling across the cosmos for nearly 14 billion years. When these ancient photons pass through a void, they're influenced not just by the void's geometry, but also by the changing gravitational potential they encounter. This is where gravitational lensing becomes entangled with the integrated Sachs-Wolf effect, a phenomenon already invoked to explain temperature shifts in the CMB caused by evolving potential wells in an accelerating universe. In the context of Eridanus, the photons passing through the supposed void would have experienced a reduction in gravitational pull as the void expanded under the influence of dark energy. Because the void's potential became shallower over time, photons would have lost less energy falling in and gained less energy climbing out, resulting in a net redshift, a slight cooling of the CMB in that direction. This could partly account for the cold spot, though, as mentioned earlier, the magnitude of this cooling remains under debate. Beyond the CMB, gravitational lensing effects could also impact background galaxies visible through or behind the void. In a typical field of galaxies, statistical analysis can detect small distortions in the shapes of distant galaxies, a technique known as cosmic shear. In the direction of a void, this shear should appear as a subtle radial stretching, a sign that light has been deflected outward as it passed through the underdense region. If the Eridanus Supervoid is real and as deep as proposed, it should produce a measurable lensing signal, albeit weaker and more diffuse than that caused by clusters. Efforts to detect this kind of void lensing are ongoing. Some weak lensing studies have found hints of demagnification in large voids, lending support to the idea that voids can influence light travel over cosmological distances. However, the signal is extremely faint, and in the case of Eridanus, results have been mixed. Some analyses detect a lensing signature consistent with a large underdensity, others find no significant signal, or results that are within statistical noise. This ambiguity continues to fuel the debate over the void's true existence and impact. There is also a temporal element to consider. Light from distant galaxies or the CMB doesn't pass through voids instantaneously. The time delay induced by the gravitational properties of the void, even if tiny, can alter our interpretations of distant cosmic distances and expansion history. While the delay caused by a void like Eridanus would likely be minuscule, it still factors into precise models of cosmic structure and the timing of light's journey across the sky. In a broader sense, the Eridanus Supervoid, if it exists, would serve as a natural laboratory for studying how underdense regions affect the propagation of light on the largest scales. Unlike clusters or filaments, which are comparatively well understood in lensing theory, voids are subtle, elusive, and far less explored. A void of Eridanus's proposed scale, nearly 1 billion light-years across, would represent the ultimate test case for gravitational lensing in the absence of mass. Whether or not the void can account for the full depth of the cold spot, its potential to bend, delay, and dim the light traveling through it provides another reason why these structures matter. They are not merely curiosities, they are part of the optical environment of the cosmos, shaping how we perceive distant light and how we interpret the universe itself. Galaxies are not isolated islands floating in space. They are products of their environment, shaped by the gravitational scaffolding of the cosmic web. In regions like dense galaxy clusters, galaxies are surrounded by neighbors, bombarded by interactions, and often stripped of gas. But inside vast underdense regions like the Eridanus Supervoid, the evolutionary story may be strikingly different. If the void exists as proposed, then galaxies within its bounds are evolving in one of the quietest corners of the universe, and that solitude has consequences. In cosmological terms, underdense regions are low-pressure environments. With fewer gravitational tugs from nearby mass concentrations, galaxies and voids experience slower dynamics. This means fewer high-speed encounters, fewer mergers, and less external disruption overall. As a result, the growth of structure in voids is delayed compared to denser regions. While clusters may see galaxies coalescing and evolving rapidly, galaxies and voids may remain smaller, more pristine, and often more isolated for longer stretches of cosmic time. This extended isolation can influence star formation. In clusters, galaxies are often stripped of their cold gas.
Another key player is the Sloan Digital Sky Survey, or SDSS, which has cataloged the redshifts of millions of galaxies over decades of observation. The SDSS's BOSS and eBOSS programs, the Baryon Oscillation Spectroscopic Survey and its extension, have provided rich datasets that span redshifts from the nearby universe to earlier epochs, allowing for detailed reconstructions of voids and filaments. While SDSS data have contributed to initial studies of the Eridanus region, its limited southern sky coverage leaves some gaps in the relevant field of view. To probe the Eridanus Supervoid more directly, deeper and broader surveys are required. That's where future missions come into focus. First, there's Euclid, launched by the European Space Agency. Designed specifically to understand dark energy and the large-scale structure of the universe, Euclid is mapping billions of galaxies across the sky in both visible and near-infrared wavelengths. With its high-precision photometry and spectroscopy, Euclid is particularly well-suited to detect subtle underdensities, distinguish overlapping voids, and resolve the spatial and redshift structure of any potential supervoid. Its southern sky coverage may directly encompass the Eridanus region, providing the clearest test yet of the void's depth, shape, and coherence. Another future powerhouse is the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST. Scheduled to begin full operations in the mid-2020s, LSST will conduct a 10-year survey of the southern sky, capturing repeated deep images of billions of galaxies. What makes LSST invaluable is not just its sky coverage, but its temporal resolution. It will observe the same regions repeatedly, allowing for variability studies, transient detection, and the construction of very accurate photometric redshifts. In the context of Eridanus, LSST could dramatically reduce the uncertainties that have plagued earlier photometric-based void studies and finally resolve whether the underdensity is real or a data artifact. On the spectroscopic side, DESI, the Dark Energy Spectroscopic Instrument, is already operational and aims to measure the redshifts of over 35 million galaxies and quasars. With high-precision redshift data, DESI is capable of mapping the three-dimensional distribution of galaxies with unprecedented detail. If DESI's coverage intersects with Eridanus, it could provide a definitive measure of galaxy clustering and density across multiple redshift slices, confirming or refuting the existence of the void. Complementing these surveys are upcoming radio observatories like the Square Kilometre Array, which will map the distribution of neutral hydrogen gas across cosmic time. SKA's all-sky HI surveys could reveal the structure of matter in and around voids like Eridanus from a completely different angle, not via starlight, but through the faint whispers of hydrogen gas stretching across billions of years. In combination, these surveys represent a multi-wavelength, multi-epoch assault on the unknown. Each offers unique capabilities, deeper imaging, more accurate redshifts, better sky coverage, and together they promise to build the most detailed map of the cosmic web ever assembled. If the Eridanus Supervoid is real, these instruments will find it. If it is a phantom, these same tools will expose the illusion, resolving the anomaly not with speculation, but with data. In that sense, the future of the Eridanus mystery is not theoretical, but observational. The next generation of surveys holds the key, not only to this singular puzzle, but to our broader understanding of how structure, matter, and mystery are distributed across the observable universe. The question that continues to loom over the Eridanus Supervoid like a shadow stretching across the cosmic landscape is this: can a void of this size, nearly 1 billion light-years across, be allowed within the framework of current cosmology? It's not a trivial question, nor is it one that has a straightforward answer. It strikes at the heart of the lambda cold dark matter model, our most successful theory for describing the evolution of the universe, and challenges how we interpret the emergence of structure in a cosmos shaped by dark matter, dark energy, and initial quantum fluctuations. According to lambda cold dark matter model,
The large-scale structure of the universe forms from tiny density perturbations in the early universe, infinitesimal ripples in the fabric of space-time, generated during inflation and later amplified by gravity. These perturbations, while random, are described statistically as Gaussian, meaning the likelihood of extreme deviations from the mean, like massive over- or underdensities, drops off exponentially. In simpler terms, the larger and more pronounced a structure is, the less likely it is to form naturally. Void statistics have been studied in great detail using large-scale simulations based on lambda cold dark matter model assumptions. These simulations generate universes and allow researchers to track how voids evolve over billions of years. The results are consistent and robust. Voids are common, but their sizes tend to cluster in the range of tens to a few hundred million light-years across. Voids larger than 300 to 400 million light-years are rare, and ones nearing a billion light-years are virtually non-existent in these simulated universes. So when researchers estimate that the Eridanus Supervoid spans 700 to 1,000 million light-years across, it forces them to confront a disturbing possibility. Either our model is missing something, or this structure is simply a bizarre statistical outlier, one that formed against extraordinary odds. Some have attempted to calculate just how unlikely such a void would be under lambda cold dark matter model. Estimates vary depending on assumptions, but one often cited figure suggests the odds are in 1 in 100,000 or lower for a void of Eridanus's proposed size and depth to appear by chance in the observable universe. That's an astonishingly low probability. It's not zero, which means it could still happen, but such a rarity would imply that we are living in a very unusual cosmic neighborhood. This brings up another philosophical wrinkle: anthropic bias. If observers like us can only exist in universes with certain properties, and we happen to find ourselves in a universe with an unusually large void nearby, is that truly surprising? After all, we're sampling just one realization of the universe. The issue becomes even more complex when we consider cosmic variance, which allows for some deviations from average behavior, but usually not to this degree. If the Eridanus Supervoid is real, deep, and coherent over its entire extent, it may simply stretch the boundaries of what lambda cold dark matter model can statistically accommodate. However, some have proposed that the void might be less extreme than it appears. For instance, the underdensity could be shallower than initially thought, or composed of multiple overlapping smaller voids rather than a single enormous one. These possibilities would reduce its statistical improbability and bring it more in line with theoretical expectations. Still, even in these scenarios, its alignment with the cold spot in the CMB remains an uncomfortable coincidence, or perhaps a signal of something deeper. Another school of thought holds that lambda cold dark matter model is essentially correct, but that new physics might be hiding in the margins. Small modifications to inflationary theory, subtle variations in dark energy's behavior, or non-Gaussian initial conditions that make large voids slightly more likely. These ideas preserve the core framework of standard cosmology while allowing for rare structures like Eridanus to emerge with less tension. In the end, the question of whether such a void is allowed within current cosmology is both scientific and interpretive. Statistically, it seems implausible, but not impossible. The answer may depend on whether we're comfortable living in a universe that, while governed by predictable laws, still permits the occasional cosmic oddity. Or it may be that Eridanus is trying to tell us something, that the model is close but not quite complete. Either way, the Eridanus Supervoid sits at a boundary, the limit of what we expect, the edge of what we can explain, and perhaps a portal into new cosmological terrain we've only just begun to chart. If the Eridanus Supervoid is ultimately confirmed as a real, coherent structure, nearly 1 billion light-years wide and significantly underdense, then the implications for cosmology are profound. Its existence would not merely be an interesting footnote in cosmic cartography, it would force scientists to rethink the fundamental theories that have long defined our understanding of the universe's birth, growth, and structure. At the center of this shift would be a reassessment of the inflationary model, the rapid expansion of the universe in the first tiny fraction of a second after the Big Bang. Inflation is responsible for seeding the fluctuations that grew into galaxies, clusters, and voids, and it's typically modeled as a process that generates Gaussian, nearly scale-invariant perturbations.
These perturbations are expected to average out on large scales, producing a universe that is relatively smooth and homogeneous when viewed across hundreds of millions of light years. But a supervoid of Eridanus's magnitude challenges this assumption. If such a large underdensity arose from initial conditions during inflation, then it suggests that those conditions may have included non-Gaussian features, or that inflation was driven by a more complex mechanism than currently modeled, perhaps involving multiple fields, as in multi-field inflation, or brief localized disruptions that allowed certain regions to evolve very differently from others. Theories like inhomogeneous inflation or models with curvaton fields might need to be re-examined or developed further to explain such extreme fluctuations. Another pillar of cosmology that would come under pressure is the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. This principle underlies nearly every major cosmological model, from Friedmann equations to dark energy equations of state. If Eridanus represents a true exception to this rule, not just a local oddity but a large-scale violation, then cosmologists might need to abandon or weaken this foundational assumption. The universe in that case may not look the same in all directions, or it may not.
One possibility is that our models are fundamentally sound but not complete, that there are subtle factors in early universe physics, such as non-Gaussianities or anisotropies, that produce rare features like Eridanus more frequently than we currently predict. Another possibility is that we're seeing the signature of some new force, interaction, or domain that violates the standard assumptions of homogeneity. Perhaps inflation didn't smooth out the universe as thoroughly as we thought. Or perhaps it left behind traces, scars even, that manifest as large anomalies in specific directions. Alternatively, and more provocatively, the Eridanus Supervoid could be a sign that our universe is not the only one, and that the cold spot and void are remnants of an interaction with another domain, another universe. In such a scenario, the alignment is not chance at all, but a consequence of deep cosmological dynamics, rooted in a multiverse far beyond current observation. This hypothesis remains speculative, but it gains weight if further anomalies are found with similar patterns or alignments. And yet, caution is vital. Humans are pattern-seeking creatures, drawn to symmetry and meaning even in noise. The sky is full of random fluctuations. Some will appear special. Without sufficient statistical rigor and multiple independent confirmations, we risk over-interpreting randomness, assigning meaning to noise. This is the central tension in modern cosmology, distinguishing the extraordinary signal from the expected fluctuation. So we must ask, is the Eridanus anomaly a whisper from the edge of physics, a hint that the cosmos holds secrets we've barely begun to imagine? Or is it a beautiful accident, a quirk in the grand game of cosmic chance? At this juncture, we do not know, but the fact that we can even pose the question, that we have the tools to observe such features, and that we are continually refining our models in response, this is the heart of science. Whether coincidence or revelation, the Eridanus Supervoid reminds us that the universe is not only vast, but filled with questions too bold to ignore. If we allow ourselves to look beyond the boundaries of established models, to peer into the more speculative and exotic corners of theoretical physics, the Eridanus Supervoid and the cold spot it aligns with take on an even stranger light. For many cosmologists, if the standard explanations fall short, then the anomaly might be a subtle fingerprint of exotic physics or early universe phenomena that we haven't yet incorporated into our frameworks. These are not mere science fiction. They are serious, though highly debated hypotheses born from efforts to reconcile puzzling data with the theoretical tools we possess or are only just beginning to develop. One compelling class of alternatives centers around cosmic textures. These are a type of topological defect, irregularities that may have formed in the early universe during symmetry-breaking phase transitions, much like cracks forming in freezing ice. Just as the universe cooled and forces separated, electromagnetism from the weak force, for instance, these defects could have been left behind, embedded into the fabric of space-time. A cosmic texture could cause a localized temperature dip in the CMB, much like the cold spot, by modifying the gravitational potential in that region and altering the energy of photons passing through.
Unlike a supervoid, a texture doesn't require a large underdensity of matter, but instead reflects a distortion in space-time itself. Cosmic texture models have been proposed specifically to explain the cold spot. They predict that a region of the sky might appear colder due to the collapse of a texture, essentially a moment when a field configuration changes in such a way that it releases gravitational energy, leaving a mark on the CMB. If this explanation is correct, the cold spot wouldn't need to be aligned with a void at all. The apparent supervoid might then be an unrelated foreground feature or even an observational artifact. This would also mean that the cold spot is unique, a one-off relic of a field transition, rather than something repeated elsewhere in the cosmos. Another exotic scenario involves non-trivial topology. In this view, the universe might be finite but unbounded, with space wrapped around in ways that allow for strange alignments or patterns to appear at large scales. Such a universe could produce preferred directions or subtle periodicities in the CMB, the kind of unexpected symmetry that might, under the right conditions, align with a void or a cold region. If this topology was just right, it could even cause the same patch of space to appear in multiple parts of the sky, subtly influencing large-scale structure and CMB anomalies alike. Then there are the even more radical ideas, such as those involving primordial magnetic fields, early dark energy, or variations in fundamental constants. For example, if dark energy behaved differently in the early universe than it does today, perhaps undergoing bursts of activity or temporarily varying in strength, it could have altered the growth of structure in specific regions, amplifying or suppressing the formation of matter in ways that mimic a void. Similarly, if early universe inflation was governed by a non-canonical scalar field, or if the inflaton field had unusual kinetic behavior, as in K-inflation models, this could have imprinted large-scale features or anisotropies into the observable universe, with effects still visible today. Some speculative theories even consider that the cold spot and Eridanus Supervoid could be signs of interaction with other dimensions. Certain models in string theory and brane cosmology propose that our universe exists on a brane, within a higher dimensional space. In this picture, gravitational or energetic influences from adjacent branes, other universes, might occasionally leak into ours, leaving behind anomalies in the CMB or matter distribution. While highly theoretical, such ideas are mathematically consistent within their frameworks, and have not yet been ruled out by observation. A final class of explanations invokes bubble collisions in the multiverse. In eternal inflation theory, our universe is just one bubble in a vast multiverse, with other bubbles forming and expanding beyond our observable horizon. If one of these bubbles collided with ours during its early stages, it could have left an imprint, a cold spot or hot spot, a perturbation in structure formation, or even a localized void where matter is unusually sparse. The cold spot could then be the scarring from such a cosmic collision, a fossil of a moment when two universes brushed against each other in a higher dimensional space-time. These exotic ideas remain unconfirmed, and in many cases difficult to test. But the very existence of the cold spot and the candidate supervoid in Eridanus invite them. If the universe presents us with an anomaly that doesn't sit comfortably within our current models, and if repeated observations continue to uphold its reality, then science demands that we keep looking deeper. Sometimes the universe nudges us toward new physics not with dramatic explosions or glaring contradictions, but with quiet, persistent mysteries that linger for decades, resisting easy explanation. Whether the key lies in cosmic textures, hidden dimensions, or other universes altogether, the anomaly in Eridanus may be a clue, not just to a strange structure in space, but to a deeper layer of reality, still just beyond our reach. To understand whether something as massive and extreme as the Eridanus Supervoid could naturally emerge in our universe, cosmologists rely heavily on computer simulations, digital laboratories that replicate the formation of structure in the cosmos across billions of years. These simulations begin with a set of initial conditions derived from the early universe, and then, using the known laws of physics, particularly general relativity and Newtonian gravity, they evolve these conditions forward in time to reproduce the kind of universe we see today. These simulations are not just impressive in scale, they are astonishingly detailed. From initial fluctuations seeded during inflation, they track how matter, both normal and dark, collapses into sheets, filaments, and nodes to form the cosmic web. Along the way, vast regions are left behind, underdense, empty spaces we call cosmic voids. Simulations like Millennium, Illustris, Eagle, and Bolshoi-Planck have all contributed to our understanding of how these voids form, grow, and interact with the surrounding structure. Within these models, voids tend to form in regions that started with slightly lower than average density in the early universe. As surrounding regions collapsed into denser structures like clusters and filaments, matter pulled away from the low-density zones, causing them to expand and become even emptier over time. This process is highly sensitive to the nature of initial fluctuations and the behavior of dark energy and dark matter. The larger and deeper a void becomes, the more remarkable it is in terms of statistical rarity. In these simulations, voids typically range from 30 to 150 million light-years in diameter, with the largest, rarest voids pushing toward 300 to 400 million light-years. These extreme cases are few and far between, and often irregular in shape. Even when simulations are scaled up to replicate volumes approaching the size of the observable universe, voids larger than 500 million light-years are exceptionally uncommon, and those nearing 1 billion light-years, like the Eridanus Supervoid, are virtually absent unless the models are pushed with exotic assumptions or altered initial conditions. That's what makes Eridanus so puzzling. When scientists try to replicate such a massive underdensity using simulations rooted in the standard lambda cold dark matter model, they often fail to produce anything nearly as large, coherent, and aligned with the observed cold spot. Some simulated universes may contain deep voids or extended regions of underdensity, but they lack the combination of depth, scale, and coherence found, at least inferred, in the Eridanus data. To create a void of this magnitude, simulations must either assume a non-Gaussian distribution of primordial fluctuations or input cosmological parameters that deviate from the standard model, such as changes to dark energy dynamics, matter density, or inflation physics. Interestingly, researchers have used simulations not only to model the void itself, but to assess whether such a structure could cause the...
In fact, when researchers have attempted to measure just how improbable the cold spot is within the standard lambda cold dark matter model, results vary. Some suggest its temperature depression is so extreme that it should occur only once in many thousands of observable universes. Others argue that if all sources of uncertainty, analysis methods, and data treatment are fully considered, the cold spot isn't so anomalous after all, perhaps just a 2 to 3 sigma deviation, meaning it's unusual, but not outside the bounds of reasonable fluctuation. The same logic applies to the Eridanus void. While its estimated size is breathtaking, the measurements are not without uncertainties. Photometric redshift errors, incomplete sky coverage, and survey limitations can conspire to exaggerate the appearance of underdensity. Moreover, when mapping such vast regions, overlapping smaller voids or chance alignments can mimic the profile of a single large void, fooling even careful analysis. The apparent match between the cold spot and the void could be a coincidence of projection, a chance alignment of independent anomalies that just happens to look connected from our perspective on Earth. This view doesn't deny that Eridanus and the cold spot are real observations. It simply proposes that they don't require new physics or exotic causes. They are, instead, part of the expected statistical noise in a universe as vast and complex as ours. Under this interpretation, no new theories need to be introduced, and no existing ones need to be discarded. The lambda cold dark matter model, with all its elegance and predictive power, holds firm. This perspective is also philosophically grounded in Occam's razor, the principle that among competing hypotheses, the one that makes the fewest assumptions should be preferred. If standard cosmology can account for the anomaly, even if only as a rare blip, then invoking cosmic textures, multiverses, or modified gravity becomes unnecessary. That doesn't mean such ideas should be ignored, but they should be approached cautiously, and only when simpler explanations fail. It's worth noting that the history of cosmology is filled with false alarms, features or signals once thought profound, only to fade with improved data or revised interpretation. The alignment of quasar spins, strange anisotropies in the CMB, or mysterious dips in galaxy clustering have all, at times, sparked excitement, only to settle back into the statistical noise of a noisy universe. So the skeptical viewpoint, that Eridanus and the cold spot are meaningful only in the sense that they test our ability to interpret randomness,
is not a denial of mystery. It is rather a call for caution, a reminder that not every shadow in the sky is a portal, and not every strange shape in the data is a message from beyond. Some are just what happens when a universe born from chance unfolds according to rules that allow and even require the occasional anomaly. And yet, in that very randomness lies a different kind of wonder. Because if such anomalies are natural, then they are not glitches in the system, they are features of the universe itself. Cosmic quirks that reflect the infinite creativity of statistical possibility. They are reminders that even in a model as precise as the lambda cold dark matter model, there is still room for the unexpected. Not because the rules are broken, but because they are being followed perfectly. To truly grasp the strangeness of the cold spot and the weight it carries in the debate over the Eridanus Supervoid, it's important to step back from the cosmic scale and ask a deceptively simple question. Just how cold is the cold spot? In a universe where temperature differences in the cosmic microwave background are measured in microkelvins, millionths of a degree, even a small deviation can ripple into profound implications. And yet the cold spot stands out not because it is absolutely freezing in any everyday sense, but because of how subtly, persistently different it is compared to its cosmic surroundings. The average temperature of the CMB is about 2.725 Kelvin, just a few degrees above absolute zero. Superimposed on this nearly uniform glow are tiny fluctuations, small variations in temperature on the order of plus or minus 100 microkelvins. These temperature ripples, imprinted some 380,000 years after the Big Bang, are the result of density differences in the early universe. Some regions had slightly more matter and gravity, causing photons to lose energy climbing out of deeper gravitational wells, and others slightly less, causing photons to exit more easily and appear a bit warmer. In this sea of micro-variations, the cold spot emerged as a region with a notably lower temperature than average. Initially detected by the WMAP satellite and later confirmed by Planck, it covers a patch of sky roughly 5 to 10 degrees across in the direction of the Eridanus constellation. At its core, the cold spot dips to approximately minus 150 microkelvins, relative to the average CMB temperature. But it's not just the depth of this dip that makes it unusual, it's also the extended cold envelope that surrounds it, and the sharpness of the contrast with its neighboring regions. In comparison, other cold or hot spots in the CMB, which are entirely expected due to Gaussian fluctuations, tend to be shallower and more symmetrically distributed. The cold spot, however, has a distinctive bullseye structure, with a central low-temperature core surrounded by slightly warmer concentric rings, and then an abrupt return to typical background temperature. This peculiar morphology adds to the intrigue. It's not just colder, it's differently cold. Statistically, the cold spot lies well within the realm of what one might consider a 2.5 to 3 sigma deviation, depending on how it's measured and what smoothing scale is used. In simpler terms, there's only a 0.1 to 1% chance that such a structure would occur due to random fluctuations in a Gaussian field. That's rare, not impossibly rare, but rare enough to warrant the attention it has received over the past 2 decades. Planck's higher resolution data reaffirmed that the anomaly is real, not an artifact of instrument noise or data processing. It exists, it persists, and it is colder than it should be. But whether this temperature difference is due to photons losing energy while crossing a massive supervoid, as the integrated Sachs-Wolf effect suggests, or due to some deeper physical phenomenon like a texture, remains unresolved. What complicates the matter is that the cold spot isn't uniquely cold in terms of raw temperature. There are other regions in the sky with similarly deep fluctuations, both hot and cold. But what makes this one special is its combination of size, depth, shape, and alignment with a possible large-scale structure, namely the Eridanus Supervoid. It is the confluence of these characteristics, not just the microkelvin delta, that elevates it from interesting to potentially groundbreaking. In a cosmic landscape where most fluctuations average out to noise, the cold spot remains a focused dip, an outlier in both temperature and structure. Its very existence invites further scrutiny, because in a universe as smooth as the early cosmos appears to have been, even a tiny extra chill can hint at forces we have yet to name. The Eridanus Supervoid, with its staggering estimated size of nearly 1 billion light-years across, is often referred to as the largest underdensity ever observed in the universe. But it doesn't exist in complete isolation. Over the past few decades, astronomers and cosmologists have identified numerous cosmic voids, vast regions of space that are conspicuously less populated with galaxies and matter than their surroundings. These voids form an essential part of the cosmic web, the large-scale structure of the universe, threading between dense galaxy clusters and filaments. While none quite match Eridanus in scale or mystery, some are still impressively large and help place this anomaly in context. One of the most frequently referenced large voids is the Botez void, sometimes called the Great Nothing. Discovered in 1981 by astronomer Robert Kirshner, the Botez void spans about 330 million light-years in diameter and lies roughly 700 million light-years away. It contains far fewer galaxies than would be expected for a region of that size, initially estimated to have only a few dozen galaxies where thousands should be. Despite its vastness, the Botez void has a relatively regular shape and fits reasonably well within the predictions of the lambda cold dark matter model, though it does sit at the higher end of the expected size spectrum. Then there's the local void, a region adjacent to the Milky Way's location in space. Though it's not as large as Botez or Eridanus, it spans an estimated 150 to 200 million light-years and plays a role in the peculiar motion of our own galaxy. Studies suggest the imbalance caused by the local void contributes to the motion of the Milky Way relative to the cosmic microwave background, an example of how even moderate-sized voids can have measurable dynamical effects. Another notable example is the KBC void, named after Keenan, Barger, and Coe, the astronomers who proposed its existence. The KBC void, discovered in 2013, is a giant local underdensity that might encompass our galaxy, extending over 1 to 2 billion light-years in diameter. Unlike the Eridanus supervoid, the KBC void is more diffuse and not characterized by a single temperature anomaly in the CMB, but it's been invoked in attempts to explain certain cosmological tensions, like the Hubble constant discrepancy. Some cosmologists argue that if we live in a large local underdensity, it could subtly affect distance measurements and lead us to overestimate the expansion rate of the universe. There are also numerous smaller but still significant voids cataloged in large-scale galaxy surveys, such as the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DES). These include hundreds of voids ranging from 30 to 100 million light-years in size, forming a sponge-like pattern throughout the cosmic web. Though individually less spectacular than Eridanus, collectively they shape much of the universe's large-scale structure. So how does Eridanus compare? It's not just the size, though the near billion light-year estimate makes it at least twice as large as Botez, and possibly more.
Parallel to the observational work, scientists are turning to cosmological simulations to test various void scenarios and assess whether such an extreme underdensity could naturally emerge in the standard lambda cold dark matter model framework. These simulations allow researchers to vary parameters like the initial density field, the behavior of dark energy, or even the geometry of space itself, and then examine whether any of the resulting virtual universes produce voids of similar scale, depth, and temperature effects as the Eridanus candidate. If simulations consistently fail to reproduce a void like Eridanus, it would suggest that something fundamental in our cosmological model may be missing, or that our interpretation of the observational data needs refining. In addition, astronomers are employing gravitational lensing studies to further probe the region. Gravitational lensing occurs when massive structures bend the path of light from more distant sources. In underdense regions like voids, the opposite happens. Light is slightly demagnified, and its path is subtly altered. By carefully measuring these lensing effects in the Eridanus region, especially using background galaxies and the CMB itself, researchers can independently confirm whether there is a true gravitational underdensity that aligns with the proposed void. This kind of analysis provides a mass-based measurement of the void, offering a vital cross-check against the galaxy count method. Some studies also focus on the CMB cold spot itself, using statistical techniques to re-evaluate its significance. By generating thousands of mock CMB maps from theoretical models and applying the same observational filters used on the actual data, researchers can estimate how often a cold spot-like feature might arise just from chance. These efforts help refine the probability that the cold spot is truly anomalous, and whether its association with the Eridanus Supervoid is statistically meaningful. Beyond empirical work, there is growing theoretical interest in testing more exotic explanations. Some physicists are developing models involving cosmic textures, topological defects, or even bubble collisions in a multiverse scenario, to see whether such phenomena could produce both a temperature anomaly in the CMB and an apparent underdensity in the galaxy distribution. These hypotheses are challenging to test directly, but they provide valuable frameworks for thinking about how early universe physics might manifest in present-day observations. Finally, looking toward the future, several upcoming surveys and missions promise to shed more light on the region. The Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, or LSST, will map billions of galaxies over the next decade, providing an unprecedented level of detail across a vast swath of the sky, including the Eridanus area. Similarly, the Euclid mission by the European Space Agency, launched to study dark energy and cosmic structure, will supply extremely precise measurements of galaxy clustering and cosmic voids. These investigations, through surveys, simulations, lensing studies, and theoretical modeling, are slowly closing in on the truth. Whether they ultimately confirm the Eridanus Supervoid as a real structure with cosmological implications, or reveal it as an illusion conjured by overlapping voids and observational quirks, scientists are leaving no stone unturned. The mystery remains alive, but so does the relentless scientific pursuit to solve it. In the grand scheme of cosmology, where galaxies number in the trillions and time stretches across billions of years, one might wonder why so much attention is devoted to one single patch of sky. But the Eridanus Supervoid is not just a curiosity tucked away in the cosmic map. It represents something more profound. It stands at the intersection of observation and theory, of anomaly and explanation, and of what we know versus what we might soon discover. Its potential link to the cold spot in the cosmic microwave background makes it far more than just a big, empty region. The cold spot is a prominent feature in the oldest light of the universe, and any alignment it shares with a structure as massive as Eridanus compels us to ask questions that dig into the foundations of cosmology itself. Is this void an echo of something primordial, seeded during inflation, or is it an accidental arrangement of smaller voids aligned in a way that tricks our instruments? Could it be evidence of exotic physics, or is it simply a rare but expected ripple in the cosmic randomness? Regardless of the answer, the Eridanus Supervoid plays a crucial role in testing the limits of the lambda cold dark matter model, the most successful framework for understanding the universe's structure and evolution. If the void can be explained within this model, it reinforces the model's resilience. If it cannot, then it may mark the beginning of a shift, a new chapter in cosmology where we are forced to reconsider inflation, dark energy, or even the nature of space-time itself. It also reminds us of the importance of cosmic variance, the understanding that the universe is not just governed by elegant equations, but also by chance. Sometimes what seems extraordinary is just the rare tail end of a probability curve. Other times, it's the first sign of a deeper truth waiting to be uncovered. The Eridanus Supervoid keeps us balanced on that razor's edge. Moreover, it demonstrates the power of interdisciplinary research. The study of this anomaly has brought together astronomers mapping galaxies, physicists simulating structure formation, theorists exploring the early universe, and even philosophers pondering the multiverse. This convergence speaks to the supervoid's true significance. It's not just about one cold patch of sky, it's about the very architecture of the cosmos and our place within it. As new instruments come online and observations become ever more precise, we may yet discover whether the Eridanus Supervoid is a cosmic coincidence or a cosmic clue. But even if it remains ambiguous, it will have served its purpose. It has challenged assumptions, sparked debates, refined models, and inspired a deeper look into the structure of reality. In science, the best questions are often those we can't yet answer. And in that sense, the Eridanus Supervoid is one of the most powerful questions the universe has posed to us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.